Okay. Hang in there? Yeah? We good? I'll take a moment to pause real fast for any questions. Do we have any questions so far? Can everyone hear me pretty well? Okay. This first set of questions that for this glycolysis portion of it, this is mostly memorization. So if you've memorized glycolysis, these should be pretty easy things to know. Now, if you don't, usually what it is, what you need for glycolysis is the intermediates, the enzymes, the structures of the intermediates. Okay, those are basic questions to ask about glycolysis. Other fact-based questions are stuff like how many substrate level phosphorylations exist, what is the net gain of ATP, so on and so forth. And probably the hardest question, which we'll get to in question 9, type of question, is some sort of thermodynamic or energetics question. And we'll explore that in a bit too. And that's probably the hardest question. Okay, so which steps of glycolysis, hold up. Okay, which steps of glycolysis require NAD plus as a substrate? We can name this step, which is step 6, right? I don't like memorizing the types of steps. He doesn't require you to remember what step number it is, but you will have to identify things within that step. So what is the enzyme used for step 6? G3P dehydrogenase, all right? Glyceraldehyde, 3-phosphate dehydrogenase. Okay. Is this the only step that uses NAD? Yes. Okay. Moving on. Which steps of glycolysis are significantly exergonic and irreversible under cellular conditions? First, third, and last, which is 10, right? Okay. The step numbers are cool to write, but it's actually I'll show you an easier way to remember this. It's basically any step that involves a transfer in a phosphate, okay, except for one of them, okay? Which steps involve sort of phosphate transfer, these phosphate transfers? What's the first one? What's the enzyme? Give me the enzymes. Hexokinase, right? PFK1, PFK1. What else? Yeah, phosphofructokinase is PFK. So PG kinase, right? That's phosphoglycerate kinase. You want me to write it out? Or do you understand it? Okay. Phosphoglycerate kinase and pyruvate kinase. Okay. Now, of these, the only one that's not reversible is PG kinase. The only one that's not irreversible is PG kinase. So that's the only one that's reversible. Okay. This is reversible. It's an easy way to remember. Anything involving a phosphate transfer is going to largely be irreversible. Okay. Yes. Question up there. No. Step state involves a so let me put it this way. Any use of ATP or ADP, so these all in some sort of way use ATP to ADP or ADP to ATP, okay? They will be irreversible except for PG kinase. The only thing, so the one that does involve a free phosphate is step 6, right? This involves a free phosphate. We'll get to drawing that in just a second, okay? What is the key regulated step in glycolysis? Step 3, or PFK1, right? Okay. During which step of glycolysis does ADP accept a phosphate group from high-energy carbon phosphate intermediate? Which steps? 7 and 10, right? The payoff phase steps, right? So which enzymes are these? PG kinase and pyruvate kinase. Sure. Okay. It'll be. You can write the step number, or you can say the intermediate to the intermediate. If you write down the step involving PG kinase, I mean, there's no other thing that uses PG kinase, right? So it'll be more specific. Do you understand that how to identify the step? It'll be more specific. Yeah. Okay. And we'll be there too. So if there's any misclarification on the question, just raise your hand. We'll clarify it for you. All right? Okay. Next question. Excuse me? Off the list. What you mean for question for subset B? Question B? Yeah, it's off. It's not there. It's reversible. Everything else is irreversible in cellular conditions. PG kinase is reversible. Okay. All right. All right. Okay. So, question back there. Yes. Hexose and glucose, it's going to be phosphohexose. It's phosphohexoisomerase. I'm positive it's phosphohexoisomerase. Yeah. Yeah.
Giants are up 9-0.
9-0. Okie dokes. I'll write it up. Actually, Sam's got it. Yeah. Okay. All right, cool. Alrighty, so next question. The next question asks, glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate to 3-phosphoglycerate is an energetically important step. Draw out the structures for the above reactions, include cofactors and substrates. Okay, you think this question might be on the exam? Yeah. Was it on the exam before? I'm going to shrug my shoulder. Probably. I don't know, right? But I'm just going to take a fair guess that this is something that's a very fair game. A type of question like this is very fair game, so expect it. All right, so let's draw out the structures. I like to just draw out the names first. So I use a mnemonic. It's this mnemonic. I'll write it down real fast. Goodness gracious, Father Franklin did go by picking pumpkins to prepare pie. So these are intermediates. There's a dirty version of it. I'm not going to say it, so you go ahead and ask your peers about it. And there's an enzyme version, which is not too bad. It's Harry Potter puked at the Grand Palace party from eating poop. That F is not included. So Harry Potter puked at the Grand Palace party from eating poop. Yeah, okay. So you have to identify, you can identify the enzymes just by memorizing it, because the enzymes have hints within enzyme names is that substrates are usually involved, the substrate is usually involved in the enzyme name, or like the process in that step is usually within the enzyme name. So it's not very hard to memorize the names without the mnemonic for the enzymes, but if you forget, that's a mnemonic you can use. All right, so we have glyceraldehyde, 3-phosphate, okay, goes to 1,3-bisphosphoglycerate, okay? So let's draw that one out first. How do you draw glyceraldehyde? What does glycerol look like? Glycerol looks like, glycerol looks like this, okay? Now, glyceraldehyde, all right? How do you make an aldehyde? Is it at the edge of a molecule, or, and by the way, these are C's. These intersections are C's. So is it at the edge of a molecule, or is it in the middle? It's the edge, right? So let's make it at the edge then. Okay? Glyceraldehyde 3-phosphate. Remember, you name the carbons like this, 1, 2, 3-phosphate. So where does the phosphate go on the third carbon? The hydroxyl, right? So that is glyceraldehyde 3-phosphate. You don't have to really memorize how to draw it. You just read it. My bad. Does that make sense? Okay, so that's glyceraldehyde 3-phosphate. Let me just reproduce that right here. Obviously, fill in everything, all the information. Be able to draw out the phosphate if he asks you for that. Okay. And what's the enzyme? Let's see. We can sort of do this. All right, it's G. It's something with G. And this is pretty easy. This is glyceraldehyde 3-phosphate dehydrogenase. What's the cofactors for this? NAD plus free phosphate, right, goes to NADH, right, and plus H plus for a placeholder. Okay, so how do we draw 1,3-bisphosphoglycerate? So using the same concept, all right, we draw glycerol again. Okay, we'll draw glycerol again. Phosphoglycerates, right? Now, anything in 8 means that it has a carboxylic acid to it, this carboxylate ion to it. So we have to put a carboxylate ion somewhere here. Where can that go? Middle or the edge? Edge, right? Okay, so let's get rid of this. Draw the double bonds. Get rid of this H. Make this into an OH. Okay? So it's 1,3-bisphospho, right? 1,3-bisphospho. That means there's 2 phosphates on the structure, right? So it's 1,3-bisphospho, which means this is going to have a phosphate, right? So let's make that into a phosphate. And this is going to have a phosphate. That's 1,3-bisphosphoglycerate, okay? What do you think 3-phosphoglycerate looks like? The same thing, right? Except this is going to be what? An H, right? Okay, so we know how to draw these structures. It's not too hard. What do you think 2-phosphoglycerate looks like? Yeah, so this one's going to be an H, and this one's going to be in a P, right? Not too difficult. All right, so let's draw a 3-phosphoglycerate up here. Okay, and then we will draw, what's the next? Yeah, so it's going to be PG kinase, right? What's the substrate here used? ADP to ATP. Right. And then we have OH, OP, H, H, H. Okay, and that's 3-phosphoglycerate. All right? Okay, so we drew them all out. What are the enzymes used here, and what are their classes? We just said it, glyceraldehyde, 3-phosphate, right? Dehydrogenase, what kind of class enzyme is that? Oxidoreductase. Okay, and PG kinase, what kind of class enzyme is that? A transferase, because it's a kinase, right? It transfers a phosphate. Dehydrogenase is an oxidase reduction. So here, how do you remember the classes? Here's the acronym I use. Lil, hot. Okay, let's go over them. What's L stand for? Ligase, isomerase, lyase, hydrolase, oxidoreductase, transferase. Okay? All right, where does the energy most directly come from to drive the substrate level phosphorylation? So where's the substrate level phosphorylation? Here, here, or here? Bottom or top? Bottom. Bottom. This is where the direct substrate level phosphorylation is occurring, right? So where does the energy come from? Between 1,3-bisphosphoglycerate and PG kinase. 3PG. Between that, where's the energy coming from to drive this? Yes, high energy acyl phosphate intermediate. My bad. High energy acyl phosphate intermediate. Okay. So what is we'll get to what isn't high energy acyl phosphate intermediate, but basically this high energy structure up here, what can we do to figure out that this is exergonic? So I'll show you an easy way to figure out if things are energonic or exergonic. I'll teach you a really easy way. So we'll draw a free energy diagram. Okay. Now, when I think about negative charges, when I think about phosphates, I think about higher energy, right? Let's think about a very classical example. ADP. ADP has 2 phosphates. ATP has 3 phosphates. Which one has higher energy? 3. 3 phosphates has more energy, right? Because there's a lot of negative charges localized right next to each other, and they're forced to be next to each other. And that's a lot of strain on the bonds. You can use that energy to drive, energetics and other reactions. So if we were to draw the free energy diagram for this, the first one's 1,3-bisphosphoglycerate. Is it higher or lower? It's higher. It has 2 phosphates, right? Now this one has 1 phosphate, so it's going to be higher or lower? Lower. So if we draw the free energy diagram, what does that look like? Exergonic. Okay, let's draw the free energy diagram. I'll just put it in the corner right here for ATP. So if we're going from ADP to ATP, is ADP lower or higher? Lower, and ATP is higher. So what does that look like? Exergonic or endergonic? Endergonic. So we know this exergonic reaction is driving the endergonic reaction, right? And more explicitly, we say the exergonic reaction. So it's this exergonic reaction from 1,3-bisphosphoglycerate to 3-phosphoglycerate, and I'll kind of put it in there, is driving the endergonic reaction of ADP to ATP. Okay. All right. So the exergonic reaction, which is 1,3-bisphosphoglycerate to 3-phosphoglycerate, is driving the endergonic reaction, ADP to ATP. And another phrase that you would want to use that would make this answer completely correct is the high energy acyl phosphate drives the substrate level phosphorylation. Okay. Substrate level phosphorylation. Questions? Moving on. All right. So question C, where does the original energy come from in the above process? All right. We already know that the direct energy came from this exergonic-endergonic coupled reaction where a high energy acyl phosphate drove the substrate level phosphorylation. But where did this high energy acyl phosphate come from? Where did we get this? Well, obviously, we have to look at the previous reaction, right? So we look at glyceraldehyde 3-phosphate. What happened to glyceraldehyde 3-phosphate to make this structure? You oxidized it, right? Okay. What part did you oxidize? Did you oxidize the first carbon, the second carbon, or the third carbon? The first carbon, right? This thing underwent an oxidation. Let's talk about oxidation and reduction for a bit, right? Whenever you have an oxidation, there's almost always a reduction, right? So you oxidize this, what got reduced? NAD to NADH, right? It got a hydride. It got electrons, right? So there's two definitions used in this class. It's the transfer of electrons, which is Leo says GER. Loss of electrons means oxidation. Gain of electrons means reduction. And the organic chemistry, I guess, version of that is more O's means more oxidized. Less O's means reduce. More H's means reduce. Less H's means oxidize. Okay, so let's look at these two structures. This has an H and this has an O, right? This has an H, this has an O. So this was oxidized. Does that make sense? Okay, so comes from, I'll put it down, comes from the oxidation of glyceraldehyde 3-phosphate. Okay, I write it a little differently because later in this course, you see a molecule that's also abbreviated G3P, and it's glycerol 3-phosphate. There's no glyceraldehyde 3-phosphate. It's confusing to use those two terms, so if I write GAP, or if you write JP in the future, just know that as a reference, okay? Glyceraldehyde 3-phosphate. What is the acyl phosphate intermediate? What's an acyl phosphate? What's an acyl? It's like a carbonyl group, right? Okay, an acyl phosphate is this. So anything that looks like this. Now, why is this important? It's high energy, right? High energy. Now, is this, let me draw something else. PEP, phosphoenolpyruvate. Is that considered a high energy acyl phosphate? I'll draw it out right here. Okay. H. Okay, is that considered a high energy acyl phosphate? This is phosphoenolpyruvate. True or false? False. It is not. This is something that will trick people, all right? Because the phosphate needs to be directly attached to the acyl group. It's not an acyl phosphate unless there's a phosphate on the acyl, okay? So this is an acyl phosphate. What is this called then? What do you call this? High energy phosphate intermediate. You just don't have acyl in there, okay? All right. Above, which are considered acyl phosphate structures? So let's look. Which ones are considered high energy acyl phosphate structures? Is this one considered a high-energy acyl-phosphate structure? No, it's a high-energy phosphate structure. It's not high-energy acyl-phosphate. How about this? Yes. How about this? No, so the only one is what? 1,3-bisphosphoglycerate. All right, perfect. Okay. Questions? And then who has 10? Why is it high energy? Because you have so many negative electrons. So you have a lot of negative charges around there. That's the first thing. Okay. And then you have a lot of electronegative atoms around each other. So there's a lot of electrons in a certain place. And the most simple, in the most simple description of that process. Yeah. Any other questions? Okay. Yeah. All right. Thanks. All right, so one more thing that I think I haven't covered, and I think I get this a lot, is what things can hydrogen bond? What things can hydrogen bond? I call it phone. Fluorine, oxygen, and nitrogen, they can all hydrogen bond to H. So if that's something you need to memorize, it'll help you memorize and identify hydrogen bonds. Are hydrogen bonds covalent, or are they weak interactions? All right, so they're not covalent. They'll never have something. If it's something like this, that is not a hydrogen bond. Okay? All right. All right, let's do this. Feedback inhibition is an example of which of the following? All right, let's. Example of what? D? D. D or B? D. Okay, D. Let's go over what this means. So, what does the term homotropic mean? Same as the substrate. Okay, so hetero means just different from the substrate, right? Allosteric, what does that mean? What does the term allo mean? Different. It means different. And steric means space. So different space from what? The active site. Okay, excellent. All right, and repression just means you repress. Okay, so feedback inhibition is an example of homotropic. So let's think about it. If it might be a true and false homotropic allosteric activation, right? Let's think about this. Homotropic allosteric repression, right? So same as the substrate, on a different spot on the enzyme, other than the active site, and it represses it. Can you imagine any substrate repressing the enzyme that it's supposed to bind? No. So that term, this totally does not make sense. And inhibition, well, this is activation, so anything that has to do with activation doesn't make sense. All right, so it must be D. Does that make sense? Okay, next question. All right, everyone see that? All right, no questions? All right, when substrate binding activates the enzyme, this is an example of, so we're going to get rid of repression, right? So repression things don't work. Homotropic allosteric activation or heterotropic allosteric activation? Homotropic, okay, for the same reasons. All right? All right, because it's the substrate. This is when the substrate binds, so it's a homotropic, same as the substrate. Can heterotropic allosteric activation occur? Yes, but it's not. It's asking for the substrate. Do people understand that? Okay. All right. This is right here. Label the given graph. Okay. What does this look like? Michaelis-Menten, right? It looks like a Michaelis-Menten plot. So what's the x-axis? Substrate concentration. What's the y-axis? V naught. Okay. What's this asymptote called? V max. Okay, so we got V max. Let's draw half V max. Where's half V max going to be? Yeah, half of V max, right? So it's the y-intercept of half of this, right? So it's 1/2 V max. All right, what does 1/2 V max also correlate to? All right, also correlates to the position of Km. So we got 1/2 V max, V naught, Km, and we got the axes. Okay. All right, cool. So this is the position at which Km can be found in correlation with the initial velocity. All right. What are the assumptions used to derive the graph above? So what are the Michaelis-Menten assumptions? Catalysis happens in a single step. I think that's what he's trying to say, right? Wait, steady state. Okay, yes, steady state. There we go. Steady state assumption. We'll do that. All right. What does steady state assumption mean? Rate of formation is equal to rate of breakdown. And for what specifically? Right? The enzyme substrate complex. Okay? All right. So what's the first assumption again? You're only measuring what? Initial velocity. Only measure. What's that? No, what it's trying to say there is that you're not measuring velocity throughout because velocity may change during the process of the reaction. You're only measuring when you initially bind the substrate what the reaction velocity is. Yeah. So what is a 3? So catalysis is a single step. So if you were to look at chymotrypsin with the multiple steps, is that a single step? No, so they're making a very big assumption there as well. It just happens in one shot. Okay? Now, so why do they do these 3 things? So they did these 3 things because they needed to simplify the enzyme world in order to understand it, right? And what are the 2 qualitative and quantitatively important things that they derive from using these 3 assumptions and their experiments? Km and Vmax. Okay, those are the 2 things that they kind of figured out using these things. All right, write the general equation that best describes the Michaelis-Menten graph. What is it? 1 second. A lot of equations, huh? Okay. Oopsies. It is V naught is equal to Vmax plus substrate concentration over Km. Sorry, this is times. Plus substrate concentration. Okay, that dot is a multiplication sign. It's a massive one. Okay. What is the more general one? Right. So a hint on how to go about studying for Michaelis-Menten and Lineweaver-Burke. Anything on the homework is completely fair game on the exam and is likely to be on the exam. So please go over the homework. There's that one question about turnover. Remember that? Okay. With K-cat and turnover, that one question, I think it's in homework 2, I believe, right? It's in homework 2. So if you haven't done it, please do it. And understand it. So anything, again, on the homework is fair game. If you don't understand it, feel free to ask one of the TAs. And also know the general enzyme theory. Right? That's very important. Expressions of the general enzyme theory was one of the questions on homework 1, right? E plus S goes to ES goes to EP, E plus P. Remember that? And then you had to write K1 times. You had to basically write the expression of, of the steady state assumption. Right? That equation was basically the mathematical expression of the steady state assumption. All right? No questions? Who's next?
For the next question, write down that.
Oh, okay, this one. Yeah, all right, so this seems very easy. This seems like a very easy question, but we should cover it. There's a reason why the TAs are covering it. You can rationalize why. This is a review session for a midterm. So, all right, let's do this. Reaction coordinate. It says, draw the free energy diagram for a general exergonic reaction. For good measure, I'll do the energonic too. Okay, so for exergonic. All right. Substrate products identify in your diagram. So for an exergonic reaction, the substrates start higher or lower? Higher, okay, and the products start, they're lower, right? And it looks something like this, right? The distance from the substrate to the product, right? What is that called? Del G standard, okay? Del G standard. The distance from the substrate to the top of the activation hill, right? That is called what? Yeah, delta G transition state, okay? But, oopsies. But this is more specifically delta G transition state from, forward, or you can say substrate to product, okay? Now, from the product to the top of the activation hill is delta G standard as well, delta G standard transition state, but it's for reverse, or from product to substrate, okay? I put it in parentheses because you can put that in lieu of forward and reverse. Have we seen this before? Yeah, we have. So know how to do this. It's not just, we're not just giving it to you for extra information, right? And it does seem obvious because you've learned this in general chemistry. Okay, so energonic looks like product to reactant. Notice, substrate to product, and substrates start lower than the product, okay? They're lower in energy. So from the product, so from the substrate to the product, is known as what? Del G standard. From the substrate to the top of the hill is del G standard transition state forward, right? S to P. And from the product to the top of the hill, it's del G standard transition state reverse. Right? Be able to draw that. Questions? Yes?
Real quick, you guys should always label your axes.
Yes. Reaction coordinate, Gibbs free energy. Okay? Always label axes. All right, moving forward. All right, last question. All right. So it says, I've seen this before, okay? Identify each of the following important biomolecules by writing its identity on the provided space. Okay. What does a phosphate, a ribose ring, and a nitrogenous base look like? It's a nucleotide, right? So this is a nucleotide. How many nucleotides do we have in here? So it's a dinucleotide, right? So nicotinamide adenine dinucleotide is the structure, right? Nicotinamide adenine dinucleotide is the structure, and it's plus. Why is it plus? Well, if we look right here, at the very top of this ring structure, the reduced version is actually this, right? Notice how it has an extra hydrogen, right? So this is when it's reduced. And if it's reduced, you write NADH instead. All right? Do you have to memorize how to draw the molecule? No, but you will have to be able to look at it and say, well, this is nicotinamide adenine dinucleotide. This is, whatever structure. All right, next one. What does this look like? ATP, right? Adenosine triphosphate. Right? Here's the triphosphate. Here's the nucleotide version of it. Basically, the entire thing's a nucleotide. Sorry. What's this in the corner? Fructose 1,6-bis phosphate. Perfect, right? Here's the two phosphate structures, and it's fructose. All right. What do I call this? It's pyruvate. It's Chicoco, right? Who remembers Chicoco from my section? All right, Chicoco. Don't forget that. Chicoco. All right. It's pyruvate. Chicoco. It's ku. Yeah. All right. All righties. You got questions? Yeah. Shh, wait, don't make too much noise. We might have really good questions. Yeah. Yes, the tautomerization is a little important. I would understand that it tautomerizes, and there are just two forms. The tautomerization helps you see how you go from the enol, which is the phosphoenol pyruvate, to pyruvate. It's enol form. It tautomerizes the pyruvate form. Keto form, which is the pyruvate. Correct. Question? No. Yes. Oh, that's another thing. I know I abbreviate it just because I'm talking, but if it asks to write it out or provide the name, please write it out in full. Okay? All right? That's it. Thank you for. Wait, one last thing.
Okay, thanks for coming. The recording of today's session will be up at podcast.ucsd.edu probably now. we'll try to post the key tomorrow. And remember Alex and Eric's all-day office hours, 12 to 7 tomorrow, Science Engineering Library. Thanks for coming.